Fluids include anything that can flow, like water, air, or even syrup. They have no fixed shape and take the shape of their container. To understand and predict how fluids behave, for instance, why does a river flow in a certain direction? How do airplanes fly? Or how does weather work? Why do we need these equations? To understand and predict how fluids behave. For instance, why does a river flow in a certain direction? How do airplanes fly? Or how does weather work? What do the Navier-Stokes equations do? They provide a way to calculate the velocity and pressure at different points in a fluid. Essentially, they tell us how fluids move and change over time. Key concepts in the equations. Velocity, how fast the fluid is moving in different directions. Pressure, the force exerted by the fluid on surfaces. Viscosity, a measure of a fluid's resistance to flow. Honey has high viscosity, while water has low viscosity. Basic form of the equations. The Navier-Stokes equations are like a recipe with ingredients that include the fluid's velocity, pressure, density, and viscosity. They look complex, but in essence, they balance these factors to describe fluid motion. In simple terms, imagine you're stirring a pot of soup. The Navier-Stokes equations tell you how the soup moves around the pot, how the ingredients mix, and how the heat affects the flow. They consider all forces at play, like gravity, pressure differences, and the soup's own viscosity. Why are they important? These equations are fundamental in engineering, meteorology, and even in designing things like aircraft and weather forecasts. Solving them helps us understand and predict natural phenomena and technology. Challenges. Despite their simplicity and concept, solving these equations for real-world problems is incredibly difficult. They are so complex that even computers struggle with them for very turbulent flows. In summary, the Navier-Stokes equations are like the fundamental rules for predicting how fluids flow and behave, combining concepts of velocity, pressure, and viscosity into a set of equations that help us understand and solve real-world fluid dynamics problems. The story of the Navier-Stokes equations is a journey through centuries of scientific exploration, a tale that intertwines the curiosity and intellect of some of history's greatest minds. It begins in the 19th century with Claude-Louis Navier, a French engineer and mathematician, who was deeply fascinated by the forces at play within flowing fluids, seeking to understand their behavior. Navier was the first to introduce the concept of viscosity, a measure of a fluid's resistance to flow, which was a groundbreaking idea at the time. Imagine honey slowly dripping from a spoon. Its high viscosity creates internal friction that resists its movement, illustrating the concept Navier was so intrigued by. George Gabriel Stokes, an Irish physicist and mathematician, picked up the baton from Navier, continuing the quest to understand fluid dynamics. Stokes further developed Navier's pioneering work, refining the mathematical representation of these viscous forces, making the equations more robust and comprehensive. Together, Navier and Stokes gave birth to a set of equations that could describe the motion of viscous fluids, capturing their intricate dance of inertia, viscosity, pressure, and external forces. Their accomplishment was monumental, laying the foundation for modern fluid dynamics. They provided a language to communicate with the universe in the tongue of fluid motion, a language that scientists and engineers still use today. These equations, however, were no simple algebraic expressions. They were complex differential equations. These equations were notoriously difficult to solve analytically except for idealized cases, presenting a challenge that continues to inspire mathematicians and physicists to this day. The Navier-Stokes equations, though daunting in their complexity, are not indecipherable. They are a mathematical representation of the physical principles governing fluid motion. Each term tells a story, a piece of the puzzle that is fluid motion. These equations break down the intricate dance of particles in a fluid. Imagine a leaf caught in a current. It's a simple yet powerful example of fluid dynamics in action. The equation describing its journey would include terms for inertia, the leaf's tendency to keep moving in a straight line, resisting any change in its motion. Then comes viscosity, the stickiness of the water, constantly trying to slow the leaf down. This resistance is crucial in determining how the leaf moves. Pressure from the surrounding water molecules also plays a role, pushing and pulling the leaf as the current shifts. This pressure can vary greatly depending on the flow conditions. And of course, there's gravity, the ever-present force pulling the leaf downwards. Gravity ensures that the leaf doesn't just float away into the air. The Navier-Stokes equations bring these forces together in a single, elegant framework. They provide a comprehensive description of fluid behavior. They tell us how the velocity, pressure, and other properties of a fluid change over time and space. This allows us to predict and understand fluid motion in various scenarios. It's like having a secret codebook to decipher the language of flowing water, swirling air, and even the blood pumping through our veins. This understanding is essential in fields ranging from engineering to medicine. While the Navier-Stokes equations are notoriously difficult to solve in their most general form, there are special cases where exact solutions can be found. These solutions, often obtained for simplified geometries and flow conditions, provide valuable insights into the behavior of fluids. They help us understand how fluids move and interact with their surroundings. One such example is the flow of a fluid through a pipe. By assuming the flow is steady and uniform, and neglecting any changes in the fluid's properties, such as temperature or viscosity, we can obtain an exact solution that predicts the velocity profile and pressure drop along the pipe. This solution, known as the Hagen-Poiseuille equation, has widespread applications in engineering, particularly in the design and analysis of fluid systems. From designing pipelines that transport oil and gas to understanding the intricate details of blood flow in arteries, these solutions are invaluable. These exact solutions, though limited in their scope, serve as important benchmarks for validating numerical methods used in simulations. They help ensure that our computational models are accurate and reliable, and provide a fundamental understanding of fluid behavior under specific conditions. They are the stepping stones that allow us to venture into the turbulent depths of more complex flows, guiding us in our quest to master fluid dynamics.